Good morning, students. Today, I will discuss about the antenna and wave propagation. There are 2 points: antenna and wave propagations, basic parameters of antenna and wave propagations, and wave propagation theory of antenna. First of all, I share a slide: antenna and wave propagations. First of all, introduce the antenna theory, basics parameters. There are basics parameters are the basics communication parameters are discussed in this chapter to have a better idea about the wireless communication using antenna. The wireless communication is done in the form of wave. Hence, we need to have a look at the properties of wave in the communications. In this chapter, we are going to discuss about the following parameters: frequency, wavelength, impedance matching, VSWR, reflecting power, bandwidth, percentage bandwidth, radiation intensity. First of all, we introduce the frequency according to the standard definition. The rate of reception of a wave over a particular period of a time is called a frequency. Frequency, all of you know about the frequency. How to represent the frequency in the mathematically? F is equal to 1 upon T. Look at the waveform between voltage and current. The frequency is so here. F is the frequency of periodic wave. T is the time period in which a wave repeats. Frequency, the unit of frequency is hertz. Next parameter, wavelength. According to the standard definition, the distance between two consecutive maximum points or between two consecutive minimum points is known as a wavelength. Look at the diagram of wavelength and denoted by lambda. Lambda is equal to C upon F, where C is the lambda is the wavelength, C is the speed of light. Next, move to the third parameter, impedance matching. This is the important parameter of according to the standard definition. The approximate value of impedance of transmitter when equals the approximate value of the impedance of a receiver or vice versa, it terms as the impedance matching. Necessity of impedance matching, necessity of matching. A resonant device is one which gives better output, certain narrow band of frequency. Antenna, such resonant device whose impedance, if matched, delivered a better output. The unit of impedance Z is ohm. Next, move to next parameter, VSWR and reflected power. VSWR, voltage standing wave ratio. According to the standard definition, the ratio of maximum voltage to the minimum voltage in a standing wave is known as a voltage standing wave ratio. If the impedance of antenna, the transmission line and circuitry do not match with each other, then the power will not be radiated effectively. Instead, some of the power is reflected back. The term which is indicate the impedance matches is VSWR. VSWR stands for voltage standing wave ratio. It is also called as the SWR. The higher impedance mismatch, higher will be the value of VSWR. The ideal value of VSWR should be 1:1 for effective radiation. Bandwidth. According to the standard definition, a band of frequency in wavelength specified for a particular communication is known as a bandwidth. The signal when transmitted or receiver is done over a range of frequency. This particular range of frequency are allotted to a particular signal so that the other signal may not interfere for its transmission. Bandwidth is a band of frequency between the higher and lower frequencies. Next, move to the percentage bandwidth. According to the standard definition, the ratio of absolute bandwidth to the central frequency of that frequency can be termed as a percentage bandwidth. The particular frequency within a frequency band at which signal strength is maximum is called as a resonant frequency. It is called as a central frequency FC of the band. There are relation between absolute bandwidth to the high frequency and lower frequency is given by FH minus FL, where FH is the higher frequency and FL is the lower frequency. How to calculate the percentage bandwidth? Percentage bandwidth is calculated done by the ratio of the absolute bandwidth to the central frequency, that is equal to the fH minus fL upon fc. Radiation intensity. Radiation intensity is defined as the power per unit solid angle radiation emitted from an antenna which is more intense in a particular direction indicate the maximum intensity of the antenna. The emission of radiation to a maximum possible extent is nothing but the radiation intensity. Mathematically, it is defined as U is equal to R square into W radiation. U is equal to radiation intensity, R is equal to radial distance, W rad is equal to power radiated. The unit of radiation intensity is watt per steradian or watt per radian square. Next, move to directivity. This is the important parameter of the antenna theory. According to the standard definition, the ratio of maximum intensity of the subject antenna to the radiation intensity of an isotropic or reference antenna radiating the same total power is called a directivity. An antenna radiates power, but the direction in which it radiates matters much. The antenna whose performance is being observed in terms of subject antenna. Its radiation intensity is focused in particular direction while it is transmitted or receiver. Hence, the antenna is said to have its directivity in that particular direction. The ratio of radiation intensity in a given direction from an antenna to the radiation intensity average over all direction is termed as a directivity. If that particular direction is not specified, then the direction in which maximum intensity is observed can be taken as the directivity of the antenna. The directivity of a non-isotropic antenna is equal to the ratio of radiation intensity in given direction to the ratio intensity to the radiation intensity of the isotropic source. This one is the mathematical equation of the directivity. Directivity is equal to the maximum radiation intensity of a subject antenna. It is the ratio of maximum radiation intensity of the subject antenna to the radiation intensity of an isotropic antenna. Here we can write D is equal to phi theta phi maximum subject antenna, phi 0 from isotropic antenna. Aperture efficiency. This is also the important parameter of antenna theory. According to the standard definition, aperture efficiency of an antenna is the ratio of effective radiating area to the physical area of the aperture. An antenna has an aperture through which the power is radiated. This radiation should be effective with minimum losses. The physical area of the aperture should be taken into the consideration as the effectiveness of the radiation depends upon the area of aperture physically on antenna. Mathematically, it is expressed as epsilon A is equal to A effective upon AP. Epsilon A is equal to aperture efficiency. A effective is equal to effective area, AP is equal to physical area. This one is the mathematical equation of aperture area. Antenna efficiency. Antenna efficiency it is also defined as the ratio of radiated power of the antenna to the input power accepted by antenna. Simply, an antenna is meant to radiate power given at its input with minimum losses. The efficiency of an antenna explains how much an antenna is able to deliver its output effectively with minimum losses in transmission line. This is observed called as a radiation efficiency factor. The mathematical expression for antenna efficiency is given below. Eta is equal to P radian upon P input. It is the ratio of radiated power into the input power. Gain. According to the standard definition, gain of an antenna is the ratio of radiation intensity in the given direction to the radiation intensity that would be obtained if the power accepted by the antenna were radiated isotropically Simply, gain of an antenna takes the directivity of an antenna into account along with its effective performance. If the power accepted by the antenna was radiated isotropically, then the radiation intensity we get can be taken as a referential. The term antenna gain describes how much power is transmitted in the direction of peak radiation to that of an isotropic source. Gain is usually measured in dB. Unlike directivity, antenna gain takes the losses that occurs also into account and hence focused on the efficiency. The equation of gain also can be written as gain is equal to eta into E into D, where D is the directivity of the antenna, G is equal to the gain of the antenna, the unit of gain is decibel. Radio waves. First of all, we introduce the radio waves. What is the radio waves? Radio waves are easy to generate and are widely used for both indoor and outdoor communications because of their ability to pass through building and traveling distance. There are some key features are, since radio transmission is omnidirectional in nature, the need to physically align the transmitter and receiver does not arise. The frequency of the radio wave determine many of the characteristics of the transmission at low frequency. The waves can pass through the obstacles easily. However, their power falls within the inverse squared relation with respect to the distance. The higher frequency waves are more prone to the absorption by raindrops and they get reflected by obstacles. Due to the long transmission range of the radio wave, interference between transmission is a problem that needs to be addressed. Now move to the next slide. In the VLF, very low frequency, LF, low frequency, MF, medium frequency band or propagation of the wave are also called the ground wave, follow the curvature of the earth. The maximum transmission range of these waves order to few hundred kilometers. They are used for low bandwidth transmissions such as amplitude modulation, radio broadcasting. And HF and VHF, HF means high frequency, VHF means very high frequency band transmission are absorbed by the atmosphere near the Earth's surface. However, the portion of the radiation called the sky wave is radiated outwards and upwards to the ionosphere in the upper atmosphere. The ionosphere contains ionized particles formed due to the sun radiation. Those ionized particles reflect the sky wave back to the earth. A powerful sky wave may be reflected several times between the earth and ionosphere. Sky waves are used by amateur ham radio operators and military communications. Radio wave propagation. Here we introduce the radio wave propagations. In radio communication system, we use wireless electromagnetic waves as the channel. The antenna of a deficient specifications can be used for this purpose. The size of these antenna depends upon the bandwidth frequency of the signal to be transmitted. The mode of propagation, electromagnetic waves in the atmosphere and in free space may be divided into the following three categories: line of sight propagation, ground wave propagation, and sky wave propagation. Let's explain one by one. Line of sight propagation. Among the modes of propagation, this line of sight propagation is one which we commonly notice in line of sight communication, as the name implies that wave travels minimum distance of sight, which means it travels to distance up to the which eye can see. मतलब जिसको हम देख सकते हैं यहाँ पे. So now that happens. After that, we need to employ an amplifier come transmitter here to amplify the signal and transmit again. Look at this diagram. This one is the line of sight propagation. Second one is ground wave propagation. Ground wave propagation of the wave follow the counter of Earth. Such a wave is called direct wave. The wave is sometimes bent due to the Earth magnetic field, get reflected to the receiver. Such wave can be termed as reflected wave. Look at this diagram. Here the wave is reflected from some obstacle present at the earth and then reflected to the receiver. Sky wave propagation. The sky wave propagation is prepared when the wave has to travel a longer distance. Here, wave is projected onto the sky and it is again reflected back into the earth. Look at this diagram. The wave is reflected from the earth and sky and reach to the receiver. This one is the sky wave propagation. There are some layers present in the our atmosphere: troposphere, stratosphere, ionosphere. All of you know about all these layers. Importance of ionosphere. The ionosphere layer is a very important consideration in the face of wave propagation because of the following reason. The layer below in ionosphere has higher amount of air particle and lower UV radiation. Due to this, more oscillation occurred and ionization of particles is minimum and not constant. Second one is the layer above ionosphere has a very low amount of air particle and density of ionization is also quite low. Hence, ionization is not proper. Look at this flow chart there, where the layer of ionosphere can be established from the following figures. Look at this distance from the earth here to troposphere, stratosphere, monosphere. All of you students, today we will discuss about the basics parameter of the antenna and some propagations, the ground wave propagations and sky wave propagations also explained through this presentation. Thank you very much.